Hey guys, hope you're doing well. I'm getting set up. Hopefully that will work. We're gonna run across. I ran from my office to here, so it's not like I went far. But let's see, what excitement do I have for you? Not a whole lot today. I'm glad you guys are coming in, hanging out. I don't know. I'm growing more fond of this every day. I miss seeing you guys. Don't forget that I have office hours. So some of you, there are office hours on Monday morning on YouTube Live. You're always welcome to come there. Unless some of you guys are like, you know what, I really love these. And I'll ask you about it in some survey stuff at the end of the semester, but they're kind of meh. But I also have Zoom office hours where you can come in and get one-on-one help, or if several of you are around, you can get several people and me help. So that's coming up. My next office hours are on Friday from 10 to 12 on Zoom. And you're like, I don't know how to find you on Zoom. So if you go to our Canvas homepage, on the front page, go to Canvas, click on the Atom thing that says Gen Chem 1, go in there. On that front page, somewhere, kind of scroll down a little bit, it should say office hours and then say Zoom, and then you can basically click on that and I'll take you to office hours. So that is always a good idea. So you can do that, or let's see, not to be a Debbie Downer or any other name. So you don't have to be a Debbie Downer, you could just be a person. But our next exam, exam 2, is in 2 weeks from today. So today we're gonna finish chapter 5. Next week we'll do chapter 6, which part of it is probably stuff that is new to you. The other part is probably stuff that you guys have seen before in chapter 6, and then we'll have an exam. So my notes say that today would be the middle lecture of the semester. I just can't believe it. I can't believe that we've made it this far in the semester. I obviously miss all of you guys, but it looks like most of you are around or around-ish. So I'm going to, let's see, where is the information I need? Oh, I remember what I was going to tell you. So your ALEKS objectives. So one of the topics this week in the videos is called Hess's Law. So we have some examples for that today. But it's not going to be in your ALEKS, but it will be on the exam. The ALEKS questions for Hess's Law are terrible. And I say that knowing that a lot of topics that ALEKS gives you are kind of crazy, but that's a whole new crazy. So make sure that you watch either that video and do some examples, or this in here. We've got 2, I think. But there will be one, and you will have to show work on the exam. So as a reward for you guys coming, I tell you things that will be on the exam. So our first question today, also hello, I'm so glad you guys are here today, is, so hold on, I was not ready, now I'm ready. So the first question is to calculate the energy required to heat 0.5 kilograms of silver from negative 3.2 Celsius to 15.6 Celsius. Assume the specific heat capacity of silver is 0.235 joules per gram Kelvin. So a couple of things about these type of questions. 1, I will always provide the specific heat capacity. It will come like this in the words, or it will also, some of the other ones, it'll just be included use the specific heat capacity of water. So please you don't need to remember that for anything else. Water you will know because you'll have used it a bunch of times, but that's about it. So in this question, we're gonna start using the Q equals MC sub S delta T. Make sure I'm in the window. So in this question, we're given a number of entities. So we have an equation. It asks us to calculate the energy. Energy is heat in this case. So we just need to find this value. So let's see what our different options are. M, C sub s, delta T. So C sub s is provided, and that is 0.235 joules per gram Kelvin. So our mass is 0.5 kilograms. So we are going to need to convert that into grams. Now, why do we need to do that? So this C sub s value is in grams. So you can either convert this to kilograms or convert this to grams. Both of them should get you to the same answer. So in this case, half of a kilogram is 500 grams. And because this is the preemptive work, I'm not worrying a whole lot about sig figs. So we will deal with those at the end. So delta T in this case is TF minus TI. So it is 15.6 minus negative 3.2, which gives us 18.8 degrees Celsius. So from here, we have M, C sub s, and delta T. So now what we're going to do is plug all of this in. And these are equal signs. Looking at the video, it looked a little like a negative sign. Definitely not. So now we're going to plug everything into our equation. So we have 500 grams. Ooh, we need to move that over because I'm going to run out of space. 500 grams multiplied by 0.235 multiplied by 18.8. So when we plug this into our calculator, we should get 2,209 joules. And so there are two sig figs in our equation because the 0.5 kilograms or 0.50, so that's going to give us 2,200 joules. And I hear there are some questions, so I'm coming along. That is true. Thank you for that, Kajal. It's posted at 5, so it'll go up later today. I have a class right after this, so true life, it's going to be a few minutes late, but that is coming. It will open at 5. So that handles that question. Nicole asks, how do we know to use Q equals M, C sub s, delta T versus Q reaction? So that is probably a super important question. So the question is, when do we use this equation, or when do we use Q reaction equals negative M, C sub s, delta T? So the key with the second equation is that it says reaction. So in this one, there's no actual reaction. So we're just heating something, so there's no reaction. When we use Q reaction, and the reason the sign is opposite, which you can't really see, is because we're measuring the water, and the reaction is the system, and if the reaction is the system, the water is the surroundings. So the other, I don't want to call it a hot tip, but the way I like to think about it is if C sub s is the specific heat capacity of water, you are always going to use Q reaction equals negative M C sub s delta T. If C sub s is anything else, you're not going to use this one. Now, Alex does some where you basically mix them back and forth to where it will have you solve for two different things, and that you set up differently, and I don't think I have an example for that, but that one would be Q of one thing equals negative Q of the other. So Ms. J asks, why did 2209 change to 2200? So we needed to account for our significant figures. So this is what you get here, and this is the 2200. that is basically the sig fig answer. But I can see that's coming in the comments, so I like it. Okay, what other questions do we have? We've got another example, kind of like this, here in just a hot second. Other questions, other thoughts? As always, if you have none, you can go ahead and write that in the box. And if you have a lot, you can write that too. Yes, I should wait to see if anyone has any questions. Yes. Okay, next. So you guys can read that if you didn't print out the worksheet or look at it. And I will erase the board so that we can move to the next. Also, I'd like to take a hot second to say really thank you for all of you who write that you don't have any questions or make comments in the chat box. It feels super cheesy to say this, but it just brings me such great joy. So, thank you very much. I really enjoy this, and it just, to be honest, brings a sparkle to a Wednesday. So let's do another problem. So in this question it says, when 1.38 grams of liquid PCl3 at 25.55 degrees Celsius is added to 342 grams of water, also at 25.55 degrees Celsius in a coffee cup calorimeter, the temperature of the solution increases to 32 degrees. If the specific heat capacity is 4.184, calculate the heat released. So this one is a little different. It does kind of read like it's going to ask you to do some weird stuff. Like this one is adapted from Alex, and I will give you some pointers on how to do that. But we'll solve this one, and then I will show you how to set up one like the one in Alex. Okay. So in this case, it is a Q reaction equals negative M C sub S delta T. And so now we need to figure out what all of our values are. So we have M, C sub S, and delta T. So C sub S is found in the equation, which is 4.184 joules per gram Kelvin. Delta T is TF minus TI. And so in this case, the final temperature is 32 degrees minus 25.55. And that is 6.45 degrees Celsius or Kelvin. So now the question becomes, what do we do about the mass? So in a coffee cup calorimeter, M is total mass. So you could almost write this as like M total or anything else, which means that we're going to add together the 342 grams plus 1.38 grams. And so when you do that, it is 343.38 grams. So the sig figs on this one are massively horrible, I'm going to be honest. So in this case, the issue isn't necessarily the values, it's that per sig fig rules, this should clear off, but I'm going to leave it in there for the equation. If this was on an exam and the question was this terrible, I would be very forgiving about sig figs. So you could have paired this here or paired it at the end. It'll all work. So now we're going to plug this in. Yep, and we're still on the board. So we have negative M, which is 343.38 grams, times C sub S, which is 4.184 joules per gram Kelvin, and delta T, which is, sorry, it's getting a little sideways, 6.45 Kelvin. Oh, that looks absolutely atrocious. let's rewrite that so that we're not quite so discombobulated. So when we plug this into our calculator, we get negative 9,266 joules, which using our sig figs, so based on the problem, we should have 3 sig figs, which is negative 9,270 joules. So what questions do we have about this type of calculation? You will see something very similar to this, both on the exam and on the weekly assignment this week. So this is our weekly assignment topic. So I don't like to say tips or tricks because that sounds like it's meant to be bad. But the ways that you can think about this, the way students get lost, is that they forget that it's not M total, or they use different numbers. Ooh, so Kajal asked, how did we round up? Yeah, so in this case, we know that we need to have 3 sig figs based on the problem. So in Gen Chem 1, in my Gen Chem 1, 5 and up rounds up, so we need to round this last decimal place to get us 9,270 joules in that way. Does that answer your question about the rounding? Or are you politely saying that I have done the math wrong? Because we all know that that's totally possible. I'll give that a second. So if this, perfect. So the other thing with these kinds of things, what we'll see in some of the next questions is Alex is going to ask you to, happy to help, to ask you to solve for different things. So Camilo asks, we only use total mass for Q reaction, right? So in Q equals MC sub S delta T, it's usually only one entity. So if you can think of a specific example where there are 2 masses for Q, I can't think of any. Because like question 1 asked where it was just the silver, there's only 1 mass. If you're thinking about one where Alex likes to ask questions like, I put this hot lead into cold water, what is the final temperature of both? In that case, you should be able to set up Q equals negative Q reaction, and that should work. But I can't think of an example about that. If you have one, you can go ahead and drop it in the comments, and I'll answer it after this one. So our next question is a 10.1 gram sample of sodium hydroxide is dissolved in 250.0 grams of water in a coffee cup calorimeter. The temperature increases from 23 degrees Celsius to unknown. The specific heat of water is 4.18 joules per gram Kelvin, and delta H for the dissolution of sodium hydroxide is 44.4 kilojoules per mole. We need to solve for TF. So this calculation is a little bit more involved, and that's okay. So let's think about where we need to go, where we have been, and how do we solve these type of questions. Because in this question, I find that students get a little lost in the it's a lot of info, and not all of it's very helpful. Let me move that down in case you can't see it. So when it gives you delta H for a reaction, we know that delta H reaction equals Q. So if you know Q per some grams, you can do Q divided by the number of moles, and that'll give you delta H for reaction. So if you have Q for a specific mass, you could divide Q divided by the number of moles, and this will give you delta H reaction. So we're going to use the topic from last week about Hess's law, not about Hess's law, about enthalpy, to be able to figure out what the change in heat is for the 10.1 gram sample by reversing this math. So we're going to take our 10.1 gram sodium hydroxide. We're going to divide that by the molar mass, which is 40 grams in 1 mole. And that gives us 0.2525 moles. So now we're going to take our delta H reaction, which equals 44.4 kilojoules in 1 mole. And then we're going to multiply that by the 0.2525 moles. And then I'm going to go ahead and convert all the way to joules, because we know in the Q equation, we're using our specific heat capacity, which is somewhere up there. It is joules per gram Kelvin, so we're going to need that to be in joules. So we're going to multiply or convert 1 kilojoule is equal to 1,000 joules. And so that gives us 11,211 joules. Now, I am of the opinion that we use all of our numbers until we get to the end and then we cut them off, right? So I like to use my sig figs at the end. Most of the time, it doesn't matter a lot. It will matter some in some of the upcoming calculations next chapter, but for this, you could go ahead and pair that back to the 3 sig figs, but let's just keep it all and go forward. So now we're going to solve for Q reaction equals negative M C sub S delta T. So we have Q reaction. Yep, if I write over here, we're good. Q reaction is equal to 11211 joules. Yes. We have a mass in this case, which is equal to 10.1 plus 250, which is going to give us 260.1 grams. And delta T, oops, let's put C sub S next. C sub S is equal to 4.18 joules per gram Kelvin, and delta T is TF minus TI, and so we are looking for TF minus 23.0. Now, I'm going to be really honest. Now we're going to do some hardcore math. That was a little overly excessive. We're going to do some hardcore algebra. So, it is my recommendation to set up all of this math and make sure that you keep track of any negative signs that you have, because if you know that a negative minus a negative equals a positive, that is going to come into play here. So, I'm going to go ahead and erase all this so that we have a little bit more board space. So from here, we're going to plug in this value of negative 11,211 joules equals negative M, which is 260.1 grams times 4.18 joules per gram Kelvin of TF minus 23.0. So now I'm going to start solving. I'm basically going to move everything but this value. And so when we do this, we get just kidding, that an 11,000 is not negative. It should be positive. So from here we get negative 10.3 equals delta T, which equals x minus 23.0. So here, TF equals 12.7 Celsius. Although Jordan's raising an excellent point, so let me think about that. This is a problem. I think I stole this question from elsewhere. I think Jordan makes an excellent point that the math that I'm showing doesn't make any sense, so let's go ahead and erase that. So this should be negative. So those cancel out, which tells us that 10.3 is equal to x minus 23.0. So x delta t equals, if you were the calculator that I brought today, hold that thought. Yeah, that gives us 33.3 degrees Celsius. Good catch, Jordan. Thank you for seeing that. So in this case, it has to do with the fact if you are solving for Q reaction where you measure the temperature of the water, I always advocate for Q reaction equals negative MC sub S delta T. In this case, you have to decide whether or not this value is negative. I will also not ask this in this way on the exam. I will ask it much more straightforwardly, somewhat similar to what you will see on the weekly assignment this week. I think this question is asking something that is outside of what I think is really important, but you will see this on Alex. So in this case, if both of these are negative, then this can be positive. You can also think about, so you could have also made them both positive, but Q reaction, I always use it as negative. Because in my mind, if you watch the video, I go through how you calculate that, and it is because if you are measuring, make sure this is in the video, if your thermometer is measuring the water, so this measures H2O. We know that the water is in fact the surroundings of the system, which is the reaction. So heat from one goes to the other. The other way to do it is to always think about assigning the sign of heat correctly. So it may be what Jordan thought about is like, okay, if heat increases, then Q reaction should be negative. So you can also do it that way and calculate it in that way. Does this make sense? What questions do we have? Did I make it worse? What do we got? So the next two questions that I'm going to show you guys are Hess's law. Now, some semesters students absolutely love Hess's law, and other semesters students think this is the absolute worst. So I think Hess's law is it's not a weird concept, but it's a lot like a Sudoku puzzle. So instead of thinking about Hess's law as this super complicated math calculation, think about it as a Rubik's Cube type puzzle. Now, I cannot do a Rubik's Cube. If you can, I'm very impressed. But the idea is to use the equations you've been provided here and here to make an equation that looks like this. So, two things I think are important. One, you are always going to be provided the equations given. You cannot do Hess's law without knowing the equations. That just doesn't make any sense. So I will always give you the equations, and they will always have the delta H associated with them. So the formatting of this one is a little weird, but I think it works okay. So what we're going to do, here's how we start. So one, I always in my mind think like, okay, equation 1 or equation 2. And don't try to work both of them at the same time. It's always tempting, but that doesn't work. So I'm going to take the first equation right up here, and I'm going to look at it, and I'm going to compare it to the equation we're trying to make. So when we think about this, we can say, okay, well, the ketene, the CH2CO gas, that molecule, which is right here, needs in the known equation is on the product side. So we need to flip that equation. Now, it gets a little tempting to try to say like, okay, what else should we do to that? You kind of either have to flip it and multiply or just multiply. So when we do this, we just need to flip it. So take one thing. So we're only going to look at the ketene molecule, and we're going to flip that, and then it will match the moles. So I'm going to flip that equation. Yes. So make sure that you guys can, let's just write. So we're going to flip number 1. And so when we do that, we get 2CO2 plus H2O goes to CH2CO plus 2O2. Now, when you flip something, the sign of the delta H flips as well. So our delta H, which is negative 981.1, is not going to be positive. You can't see that right there. So we also flip the sign of delta H. So for the second one, what do we need to do? So when we look at that, we're going to, it looks like everything's kind of in the right place, except for a CO2, which we're not really sure what we're going to do about that. But the methane that we need, which you can see right here, needs to be 2 moles of that in order to match this. So for equation 2, we're going to multiply it by 2. Number 2 by 2. So now we're going to have 2CH4 plus 4O2 gives us 2CO2 plus 4H2O. So our delta H is going to equal 2 times negative 802.3. So from here, you need to actually sum this up and make sure that you got the equation of interest over here. I always like to put my arrows in the same place because it's going to make my life much easier. So we're going to have our 2CO2 plus H2O plus 2CH4 plus 4O2 is going to produce CH2CO plus 2O2 plus 2CO2 plus 4H2O. Now we need to cancel anything that's observed on both sides. I think the red marker shows up, so I'm going to use that. From here, we want to cancel anything we see on both sides, okay? 2 CO2s. Hey, we see that on both sides, which is great, because it's definitely not in our final equation. Adios. Okay, so that's good. H2O. We have 1 H2O on the left and 3 on the right. So we're actually going to get rid of, or 4 on the right. We're going to get rid of this and convert that to a 3. 2 methanes, but we have 4 oxygens and only 2 on the right. So we're going to get rid of that and make this a 2. So I will then rewrite mine to say 2CH4 plus 2O2 gives me CH2CO plus 3H2O, which is what we were looking for. So that means you've done all the right things. So delta H in this case is positive 981 plus 2 times negative 802, which gives us negative 623.5 kilojoules. So how do we feel about this Hess's law example? What do we think about these types of calculations? What questions do we have? And if you're thinking like, okay, but like how much work do I really have to show? You have to show this part. You can do this on top, like up in this part of the equation. So you can do that, but you need something more than just delta H equals the value, okay? Because don't forget, I will give you partial credit for any extra, like not extra work, but if you do something wrong, I want to reward you for what you get right. So far, it seems you guys like Hess's law. Me too. Okay, let's move that over. So in this case, we have an equation. So it says, calculate delta H reaction for 4 ammonia plus 5 O2 goes to 4 NO plus 6 H2O from the following data. So this one is kind of like a level up because now there are 3 equations. I will tell you that sometimes both the questions in the book, I think the ones on the worksheet, and I know I've done it on exams, it might give you 3 equations, but you may not have to use all 3 equations. So let's think about what to do in this case. So Ms. J asks, do we need to include states? You don't. You should keep track of them in case they're changing, but I don't in this case because we're using known equations. So you do not have to include the states. If you need to, it will say, like, make sure that you include those on the exam. Good question. So from here, when I saw these like in the videos or anything else, I assigned values like equation 1, 2, and 3 to help me keep track. So I usually start with the top one just because it's the top one. And on this one, I look at it and I say, okay, it has 2 NOs. Well, I'm going to need 4 NO in this equation at the top. So I'm going to take number 1 and multiply by 2, which gives us 2 N2s plus 2 O2 goes to 4 NO. So delta H is going to be equal to 2 times negative 180.5 kilojoules. So for the next one, N2 plus 3H2 goes to 2 NH3. Well, the ammonia is on the reactant side. So we're going to need to flip that and multiply by 2. So we're going to flip 2 and multiply by 2 to give us 4NH3 goes to 2N2 plus 6H2. And delta H is going to flip signs and multiply by 2. So it's going to be 2 times positive 91.8 kilojoules. So for number 3, it's H2O2 and H2O. So that one, we're going to need to multiply by 3 to get the 6 in the equation that we're trying to make. It's right there. So we're going to multiply number 3, multiply by 3, which gives us 6H2 plus 3O2 gives you 6H2O. And delta H in this case is 3 times negative 483.6. So in this case, as we total these up, I'm going to show you the other way that you could think about this. So this way works really well if all of your arrows are lined up, because we know everything on this side is a reactant, everything on this side is a product. So I'm going to look and cancel out anything that we see on both sides, even in different equations. So I see 6 moles of H2 gas on both sides. I see 2 moles of N2 gas. And so nothing else is duplicates. But over here, we have 3 moles of O2 and 2 moles of O2, which will be added together. So we're going to end up with 4NH3 plus 5O2 gives us 4NO plus 6H2O. So this equation looks identical to what we were shooting for, which is a good sign. So from here, our delta H of this reaction is equal to negative 1,628.2 kilojoules. And so don't forget, because this is addition, the only thing that matters is how many decimal places we have. So we don't need to round this because we're not multiplying. So it will just be 1,628.2. Well, negative 1,628.2. So this is Hess's law. What questions do we have about Hess's law? How do we feel about Hess's law? Is Hess's law as intimidating as you might have felt like it was before? I love Hess's law. I just love it a lot. Yes. I like it when you guys tell me, like, oh, this is easier than you expected. I like Hess's law too. I like Hess's law in the next part, the pizza formation. I like that one a lot too. Sometimes I find that calorimetry, this first couple of problems, meh. It's not my favorite chapter 5 topic. These two I think are much more fun, but I like a good puzzle. So this goes here, and where did that go? Y'all make me so happy sometimes. Okay. So the next, how many questions? Next 3 questions are heats of formation. So I'd like to give you guys the basics first. This one, I like this question. It's a little different than the others. But you are always going to be given a table that looks kind of like this. Maybe not exactly like this, but something very similar to this. In Alex, if you looked at the solubility table, because it has like that resources tab, there is also a heats of formation table in there. So I tell you this because when you do the homework, if you don't know where the tables are, it's going to be really hard to solve this. So in class, well, not in class, on YouTube Live, on the exam, this is not the weekly assignment topic, but in any of those cases, I will provide you a table. There's also a small table in your book, or appendix, I think it's appendix C at the end of the book, has like a whole list of these. So if you're trying to do a worksheet or something else, you're gonna need some tables that look like this. But I've obviously added these today because that's exciting. Okay, so this question asks, given the following standard, meaning the equation that's provided, copper oxide plus H2 gas gives us copper solid plus H2O. And so that tells us the delta H reaction is negative 129.7 kilojoules. So we'd like to know, using the standard enthalpy value for water, what is the delta H naught F for copper oxide? So to use delta H naught F, delta H reaction is equal to the sum of the delta H naught F for the products minus the sum of the delta H naught F for the reactants. So this is, at heart, addition and reading stuff off of tables, which everybody likes that, right? So in this equation, we're given delta H reaction. So delta H reaction is going to be negative 129.7 kilojoules equals delta H reaction. Now, to calculate delta H reaction using the heats of formation, your equation would look something like this. So it's going to be products minus reactants. Yep. Yeah, you can't see that. So we'll just write a big P minus R. So for the products, it's going to be the delta H naught F of copper plus the delta H naught F of H2O minus the reactants, which is the delta H naught F of copper oxide plus the delta H naught F of H2. Now, your table only has one value, and we are solving for something else. So if you look at this equation, there are 5 things. I'm asking for one of them, but I only gave you 2. Feels like a trap, right? It's not. But we have to remember that the delta H naught F for any element in its native state is 0. So, solid copper, that's 0. Okay, well that's exciting. Copper oxide we're solving for, and H2 is also 0. Okay, well this is now looking like a math problem that we could actually solve. So we're going to take our negative 129.7 equals the delta H naught F, which is negative 286 kilojoules, minus delta H naught F of copper oxide. And this is what we're looking for. So from here, we're going to take our negative 129.7. We're going to add, well, I'm going to subtract this from both sides. So we're going to end up with 156.3 equals negative delta H naught F of copper oxide. So the delta H naught F of copper oxide is negative 156.3 kilojoules. Yeah, double checking all my math. So what questions do we have about this thing? Let me try to move to where you can actually see the math. So when we think about this right here is just keeping track of this negative sign as we move it around. So do we have any questions about this? I'm not loving that my face is covered by that, so we'll move it over here. Do we have questions about this equation, this problem? Do we think it was easy? What are your thoughts? Let me know. like there's any questions. But I'll give you guys another couple of seconds. If you've got something percolating around, go ahead and drop it in the comment box. So Jordan asks, so the formation of copper oxide releases heat. It does, because copper plus oxygen to make copper oxide is going to release heat. Or you have to, in that case, set that up. But for these type of values, you should never change the values provided in the table. So whether it's, so delta H naught F equations come out of this like fat book at the end, in that case. Jordan, no. Some of them will be positive. We will not see any today, but if you look in the values, some of them are. And as Billy Ann asked, what about the second part of the equation? I kind of forgot that part, so we'll go back and do that part because I forgot. Yes, I think this part makes a little bit more sense this week. I think this is a topic where we're kind of putting all the pieces together, and the pieces start to fit. I like to do puzzles. I feel like we've built enough of the puzzles that's what's left fits into the puzzle pieces. So I'm glad you guys are enjoying it too. So as we were rightfully pointed out, we forgot to complete part of the question. I'm going to go ahead and make this box go away because we don't need it. So the last part of the question is, what is the enthalpy change if 3.203 grams of copper is created? So we know that delta H reaction is negative 129.7 kilojoules per, and based on the reaction, 1 mole of copper. So then we're going to take our 3.203 grams of copper. We're going to divide by the molar mass, which I totally forgot my periodic table. So I think it is 63.9 grams and 1 mole. But can someone actually confirm, or let me ask that different question. Will someone confirm that this is the molar mass of copper for me? 3.203 divided by 63.99. No one said anything yet, so. And that equals 0.0500. Okay. I got an I think so we're going to roll with that. Moles. So if that is not the right mass, we'll adjust accordingly. So then I'm going to multiply this by 0.0500. Oh, so close. Let's fix that real fast. We haven't quite finished. 63.55. 0.0504 moles. Then our 0.0504 moles. So that equals and the enthalpy change is negative 6.537 kilojoules based on that number of grams. But I feel like someone asked a question. So Catherine asked like a while ago, why did we change signs at the end? And I just realized I didn't answer that. So Catherine, when we solve the math that I've now erased, so I'd like to apologize for that. But we get that positive 156 equals negative the delta H naught F of copper oxide. Now, this was like negative 286. So this negative sign right here needs to come forward when we do this calculation, and it asks for the delta H naught F of copper oxide, so it becomes negative 156.3 in that case for this equation. So it's not that we changed the sign, it's that we basically kept track of the sign from here and transferred it to the other side of the equation. That was a really good question that you asked a while back. But why is it negative delta H? So the negative delta H, it's not necessarily a negative delta H. It's that in this equation, when you subtract products minus reactants, there's a negative sign because it's a subtraction value. So it isn't necessarily that it's negative delta H, it's minus delta H, which is a negative sign over that, right? So it's that we brought the negative sign with it. If that, like, I feel like it's a little confusing. Is this helping in any way, shape, form, or fashion? Good. I'm glad I remembered your question and was able to answer it. So our next question is, given the following data in the table below, which I'll pop up in just a second, calculate delta H for this reaction. So move that down a little and put that right there. So in this problem, we're also going to use our delta heats of formation, or delta H naught Fs. So we know that the delta H reaction, is going to equal delta H naught F of H2SO4, and in this case liquid, minus delta H naught F of SO3 gas plus delta H naught F of H2O liquid. Now, all in all, this is pretty straightforward, but you'll notice that there's a whole bunch of like other random stuff in this table. In chapter, or in the previous section for Hess's law, I said you don't really need to keep track of the states. In this case, you do. Because it's possible, and frankly very likely, that on the exam I would include H2O as a gas and a liquid, because they have different delta H naught F values. So in this case, we have SO2, SO3, SO2Cl2, a whole bunch of, I don't want to call them random, but things that kind of look like stuff in our equation. So to calculate delta H, it's going to be negative 814 kilojoules minus negative 396 plus negative 286. So when we plug this into our calculator, we should get negative 132 kilojoules. So what questions do we have first? And then I will tell you the places where I see students make mistakes the most often. So far I'm not seeing any questions. So I'll tell you about the mistakes that I see. So the biggest mistake, no question, is that this negative sign, so you'll notice I've used brackets around this section where there are two values. You need to make sure that the negative, so it's minus all of this. And so you need to make sure that your negative sign here doesn't become the minus sign because that will give you the wrong answer. So that my suggestion is to do that kind of stuff. And on your work, on the exam, right, where you show your work, that will be super helpful because then I can see, okay, here's where you went wrong in this way. Delta H reaction is reported usually as just kilojoules because you have to associate what it is. So in this case, delta H reaction is just kilojoules, or it can be written as negative 132 kilojoules per 1 mole of SO3 water or H2SO4. But that per mole designation is not mandatory for a delta H reaction. Delta H not F, these values, yep, in the table, are kilojoules per mole. But in a heat of reaction, it is not always reported, it's almost never reported as kilojoules per mole. Good question though, Jordan. So it looks like you guys don't have a lot of other questions. So also this says number 9. I just lost count. It's only number 8. So again, it says using the data in the table below, calculate delta H reaction for the reaction of 2 silver sulfide plus oxygen gas gives us 2 silver oxide plus 2 sulfur. So delta H not F in this case is going, not a sum, we don't need that. It will be 2 times delta H not F of silver oxide plus 2 delta H not F of sulfur minus, in this case, 2 delta H not F of silver sulfide plus delta H not F of O2 gas. So in this case, we are going to cancel out anything that is in its standard state. So sulfur and oxygen are both 0. And so now we can plug in our values, which are 2 times negative 31.0 minus 2 times negative 32.6, which gives us 3.2 kilojoules. So this, nobody likes to be missing their face. So in this equation, sorry that moved around pretty quickly, it's relatively straightforward. Now you may say that the native state of sulfur is not actually just sulfur, it's sulfur 8. We're going to ignore that in this question if the database didn't actually have the one I needed. But in this case, if it is an element alone, more than likely it's in its native state. Not always, but you can mostly make that assumption. So what questions do we have about delta H not F? Heats of formation, what I'm hearing is pretty simple. Hess's law, pretty simple. And calorimetry, only mildly tricky. It's not super complicated, it's not super hard. So what questions do you guys have? This is the last question for today's help session. What other questions do you guys have? Thoughts? Otherwise, I'll see you same time, same place next week. I'll move this back over here in case you were looking for that. Any other questions? Any other thoughts? Questions about any host of things. Doesn't sound like you guys have a lot of questions. Don't forget the exam is due, not due. And there will be way more information coming. It will be the exact same like format as last time. It is open notes, so make sure you have notes. I will provide any of these types of tables that you need on the exam, so you'll not have to look at databases for that. I'm glad you think this is pretty simple, Kachal. I do too. It's taken me a while, but I realized that all of this is just a puzzle. So, anybody else have any other questions, any other thoughts today? It doesn't look like there are. So I'm gonna let you guys go. Let you go. It's YouTube Live. But I'm gonna let you guys enjoy the rest of your afternoon. Y'all have a fantastic day, and I will talk to you guys later. Bye, guys.